All right, so hello. We're officially starting now because we're recording. So the first thing I wanted to mention is I emailed everyone this morning about like the final exam review and everything like that. I was looking over the final exam review handout from last semester, and it wasn't as nice as I would have liked it to be, so I am completely remaking it. And I'm a little more than halfway done. It took a lot longer than I was expecting, so I wasn't able to send that out in today's email because I did want you guys to know the date and time of the review and have the what to study guide thing. So I sent you all of that, and I will be sending you the review handout sometime this week before Friday, obviously. So if you have any questions about that, please let me know. The exam review is this Friday from 4 to 7. I did do a 3-hour slot because the final exam review always takes a long time. And I'm going to give you a minute to ask questions and whatnot while I share the screen and just get going. I'm going to open up to what we did last time. As always, let me know if you have any questions, comments, concerns regarding what we covered last time. And while you guys do that, I will show you the best thing I've ever purchased. So I'm sure you guys have seen like the octopuses that you can like, the plushies that you can flip inside out to show your mood. So I got an axolotl and it's mad. Now it's happy. And this is now the new mascot of Orgo2. I just thought you should all know. All right, that was my irrelevant thing. It is so cute. Look, aw. Happy to see you guys. Okay, that's my random thing of the day. Okay, so it doesn't seem like anyone has any questions. So last time we talked about tautomerization and racemization. We talked about how tautomers are a pair of isomers that can interconvert through a reaction. So we need acid or base present. And we also said that the enolate was the intermediate for that. And it's called an enolate because it has a double bond and a negative charge and an alcohol. So it has all those different components in it. We then talked about the racemization, which was essentially the same exact reaction, except we had to think about what would happen if we had a chiral center present. And so we know that if we had a chiral center to begin with, and we did this reaction, if we went backwards in the reaction, we had to get a racemic mixture because we have no way of choosing at this point where the hydrogen will add because it is planar. So that's all we really did last week for chapter 18. And I didn't write it in here because we talked about it. We did answer this question. So as a little summary, we're going to fill in the enolate diagram. So again, the enolate is the intermediate structure for this tautomerization. And one possible structure is when we have the negative charge here and a double bond to the oxygen. And we know that the resonance structure would be moving this this electron here to form a double bond and pushing this double bond up. So once we do that, we get a negative charge on the oxygen, a double bond here, and of course we have our hydrogen present. So these are resonance structures. All right. So we are going to skip this question for now because it's something Dr. West used to cover, but I don't believe he covers it anymore. He told me not to worry about it. So we will skip it for now. And if he covers it at some point before the final, we can talk about it. But for now, bam, we're just going to skip right past. The next thing we are supposed to talk about is acidity. We talked about acidity a lot this semester. So let's quickly go through and add anything that we didn't talk about thus far. So, a little note here, cardio. If you remember from Orgo 1 and what we talked about earlier, so we know that C is for charge. If we have a plus charge, it's more acidic. If it's a negative charge, it's going to be more basic. And then we talked about atom. So we know that more electronegative equals more acidic. As far as R for resonance goes, we know that the more resonance there is, it's more acidic. And with that, we know that a triple bond is more acidic than a double bond, which is more acidic than a single bond. Something that's new that we added is alpha position is acidic. And does anyone remember why the alpha position is acidic? And it doesn't have to be like a long answer. It could just be like a one word, short and sweet, whatever you remember from last time. Bam, bam. Awesome. So someone said because of the ability of the hydrogen to move. So yeah, the hydrogen is able to be pulled off more easily. And the reason for that is because you have the idea, but I'm going to say it in like the key terms kind of version. So the alpha position is acidic because it is the allylic position, aka resonance stabilized. So this is pretty much all you need to know for acidity for this semester. So let's zoom out. So here we see a triple bond, we see two carbonyls, and we see a carboxylic acid. So first we need to make sure we're all on the same page and know which hydrogen we're talking about. And so anytime he asks you a question like this, you're supposed to know, or you're supposed to assume that you're going to look at the most acidic hydrogen on each molecule. So I've made those all in red, and this one I just circled because I didn't want to like re-outline it. So the first one that we are going to kick off, so we're going to say it's the least acidic, would be answer choice B. And the reason is this one has two oxygens. This is a carbonyl, so it's the allylic position. This one is a carbonyl because the allylic position. And this is just a triple bond. So the triple bond is automatically the least acidic of the group. And when we're talking about like atom, right, and resonance, this one is directly connected to an oxygen. And we know that that oxygen has resonance with the other oxygen. Whereas both of these carbonyl groups only will have the resonance here. So it's the allylic position, it has resonance, it's great, but it's attached to a carbon, whereas this has the same resonance, but it's attached to an oxygen. So automatically, which one is going to be more acidic? A or C and D? A, absolutely. So now we're pretty much just figuring out what the order of the two middle ones is. So before I explain it, does anyone want to guess which one's more acidic, C or D? Bum, ba-dum, bum, bum, ba-dum, ba-dum, ba-dum. Okay, so it is going to be C, and the reason is we look at these and they look like pretty much the same thing, right? The hydrogen is on a carbon, which is attached to a double bond, but here we have one carbonyl. Here we have two carbonyls. So yeah, like just like someone said in the chat, it's having more allylic position. So this one is allylic. This one is excuse me. This one is allylic times 2. So this one has to be more acidic. So we're going to say the order is A, C, D, B. All right. So wink, wink, nudge, nudge. He's probably going to give you something like this and ask you to pick the most acidic hydrogen. And I'm going to show you like the quick way to do this, right? And when we look at it, first thing we notice, there's no like OH or anything. So all of these are carbons, right? So first of all, we see that this and this, or you know what, let's get rid of F. This one has no resonance, nothing. It's all on its own, randomly in the corner. This is not important. So then we see this is allylic, this is allylic, this is allylic, this is allylic. Versus this one is just a triple bond. So we get rid of it. This one is just a double bond, get rid of it. So now we have 4 allylic positions, right? Do you have any guesses as to which one? Okay, so someone said what makes D not allylic, and that's a pretty good question. So as we talked about last time, allylic just means being adjacent from that carbonyl or any double bond really. In this, all of these hydrogens are directly on a double bond. And so they're almost on the allylic position, but that's really the vanillic position. Oh my goodness. I absolutely didn't spell that right. I'm not even going to pretend that I did, but you know what I mean. All right, so between A, B, C, and D, we're going to pick off the bad ones and figure out which one is the best, right? And so we know the more resonance, the better. So we can see this guy only has 1 carbonyl. This guy only has 1 carbonyl. So we get rid of those 2. And then B and C. So C is tertiary. B is tertiary. But why is B better off than C? What do y'all think? Yes, so it's attached to the benzene. And so this is the benzylic position. Plus allylic times 2. So this guy is stellar, and that is going to be our most acidic hydrogen. So I'll leave this up for a second. That's all there really is to acidity. Is there any questions? I can feel a sneeze coming, but it won't get out of my face. Ow. All right, so it doesn't look like there are any questions, so let's just keep moving right along. All right, so this chapter has a couple reactions. So I believe there's 4 or 5 different reactions that we're going to go through, and it feels like a lot, but I promise it's not that bad. So we're going to try to get through as many as we can today, and usually I show you like the whole reaction mechanism, and then we go back and we like do a summary. But since we are so close to the final, I was thinking of just showing you guys like the short versions of these. Does anyone have any objections? Sounds good. Okay, cool. I didn't think anyone would have any big objections, but just in case, you know. So, halogenation. We've done a bajillion halogenations before. So this one is going to be base catalyzed. So we have OH minus. And we have alpha 1. And we have alpha 2. Which hydrogen is the base going to steal? Alpha 1 or alpha 2? Alpha 2, that was lightning fast. You guys are definitely getting the hang of it. Okay, so the base is going to steal this hydrogen. And so we are going to get a negative charge here. And once we get the negative charge, what do we have here? What is this molecule called? Yes, the enolate. All right, so at this point, we have H2O and we have Br. And essentially, this is now the nucleophile. So this negative charge is going to come in here, attack the bromine, kick that off, and we get, bam. Oh, sorry about that. Bam. And yes, we're left off with a Br minus. Again, we're doing the short version, so we end up with OH minus again and HBr. So that's a great question. So I didn't color code this. I got lazy. I apologize. This hydrogen was stolen by the OH, and we made H2O. And then from this H2O, the Br minus that we made stole one of the hydrogens and turned into HBr and OH. So here, I'm gonna the Br is gonna steal a hydrogen, give those electrons back, and we get that. I didn't want to erase it and redraw the whole thing, so hopefully this makes a little bit more sense. So in between this step and this step, the hydrogen is being stolen from the H2O and making HBr. Oh, I see what you mean. So, okay, this hydrogen is still here. I just didn't draw it. So one of the hydrogens is still there. The other one was stolen. I misunderstood. That's my bad. Okay, so once we're at this point, well, I could say, oh, do we think the reaction is done? But at this point, you guys know the reaction is never done. So since we have more base and this is acidic, we can think by adding this Br, did we make this hydrogen more or less acidic? What do we think? More or less acidic? Bow, 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 bow. Ba-da-bow. It's okay if you're wrong. Just take a guess. Thank you, somebody, for guessing. So yes, it will become more acidic. The reason it's becoming more acidic is because this bromine is an electron withdrawing group. So now it's allylic and we have an electron withdrawing group. So this bond gets even weaker, even more acidic. And at this point, we're able to steal a hydrogen one more time. And it's basically going to undergo the reaction again. And so we're going to end up oh my goodness, that would be so cool if you stopped. All right. So now we steal a bromine from HBr. And we end up ta-da! So essentially, you can just think, if you see a ketone and you see Br2 plus base, you're going to exchange both of those alpha hydrogens for bromines. However, if we do this in acid or just regular old H2O, we have to, I'm going to redraw this H2O just so it's like easier to work with. So since it's an acid catalyst, first step would be to go ahead and protonate. Once we protonate, we get OH plus. And now that we gave that a plus charge up here, all these electrons are trying to go there and make the charge better or neutral. And so these hydrogens become more acidic. And so now we can take off that hydrogen. So please notice that extra step we had to do. So once we finally have our negative charge here, we're going to attack Br2, and we get HBr. And last but not least, we get rid of that plus charge by deprotonating. And at this point, we don't have any base left. All we have is acid. So we have HBr and we have H2O. And that is not strong enough to do this reaction again. So the difference here is base catalysts substitutes as many times as possible. Whereas the acid catalyst only adds 1 Br. So adds multiple BRs. I'm not going to do an S because that looks weird. I'm so sorry. So any questions about the bromination so far? Okay, one thing I will add, in the base catalyst example, we're going to say it substitutes as many times as possible. And what I mean by that is it's going to substitute every alpha hydrogen on one side. So you're not going to exchange all of these hydrogens. You're going to pick between alpha 1 and alpha 2, which one is more substituted. You're going to pick the most substituted side, and you're going to replace all of those hydrogens with bromines. So for example, if we had a ketone like this, we only have 1 alpha hydrogen on the most substituted side. So in this case, we would only add 1 bromine. If we had something like this, where they were identical on both sides, doesn't matter which side you pick, but you are only substituting one side. Someone said, oh, that makes sense. Good. Okay. So a lot of people have trouble with like figuring out where to put what with acid versus base. So hopefully this is pretty okay so far. I'll leave it up for a moment. And then we're going to move on. So I want you to think, we did an example where they were exactly the same. We did an example where we had a secondary, and we had an example where we had a tertiary. What happens if we have only one side that has an alpha hydrogen? So in this example, this alpha carbon has no hydrogens. So we only have one side available. Or what if we have something like this, where both sides are exactly the same, but we have 3 hydrogens available? Well, that takes us to our haloform reaction. So the haloform reaction is a specific type of base catalyzed halogenation. And we do that when there's 3 alpha hydrogens on the same side. And that is either the only or the best or more substituted side, if that makes sense. And so the way this reaction happens is, at first, it's going to be the exact same steps. Okay, yes, I can restate, excuse me, before I move on. So we're going to do this reaction when we have either one side completely blocked and we only have a primary carbon on the other side, or when both sides are primary. Because for this reaction, you need to have 3 alpha hydrogens and base catalyst. All right, so the first couple steps are going to be exactly the same as the last ones that we did. So the OH minus is going to steal that hydrogen. I can't draw benzenes to save my life. So we have two hydrogens left here. We have a negative charge. So what did we form? What is the name of this molecule? The enolate. Cool. Just making sure. So the enolate is going to be the nucleophile. It's going to attack. And we are going to add a bromine. Woohoo. So exciting, right? So clearly we're not done, because why would we ever be done? We have, oh, my bad. So we have two more hydrogens present, and I told you the base catalyzed reaction is going to take all of these hydrogens. So we're going to do that same exact reaction 2 more times. So I'm just going to write times 2 so we don't have to do a bajillion steps. And we end up with this guy. In my opinion, this is really ugly. We don't like that. How do you guys feel about this? Do we feel like it's a happy camper? Are we done with the reaction? Probably not, right? Because why would we be? So fun stuff. We are not done with the reaction. This is such a strong, withdrawing group that it's actually going to act like a leaving group. So let's see what we possibly have left in solution, right? So we have excess of this. So we have more Br2, but the Br2 is not really useful. This OH minus, though, could be useful. Oops, I am so sorry. Sorry about that. So this OH minus, since it's negatively charged, it can be a what or a what? A nucleophile or a base, exactly. So it can't be a base because there's nothing really here to take. But this almost looks like a chapter 17 problem, because I just told you this whole ugly thing is going to be a leaving group. This is going to be a nucleophile, and it's going to attack here and kick off the leaving group. So what we're going to end up with is oopsie, let's just go back. Oh my goodness. Okay, so we keep that carbonyl, and we replaced that group with an OH. As if this wasn't annoying enough, you will have to know that the side product here is C minus Br3. So this is actually going to be in equilibrium with this. So either of these could be the correct answer. So if you see an O- in the answer choice, don't freak out. These two are pretty much exactly the same thing. All he's trying to tell you is that sometimes this negative charge will steal the hydrogen, sometimes this oxygen will steal it back, so this is in equilibrium. I know this was an ugly one, but I want you guys to just think of it as 3 alpha hydrogens gives you this guy, and then you get a carboxylic acid. So I'll even give you a different one. So this looks different, but again, it has 3 alpha hydrogens. We have Br2 and base. Gives us an intermediate that looks like so. Oopsie. That looks like so. Does anyone want to take a guess at what this guy is called? Hint, look at the title of the reaction. Haloform, exactly. So the intermediate is a haloform, and eventually we end up with a carboxylic acid. So this is the summary. I know that's an ugly one, so I'll give you a moment. Does anyone have any questions? So yes, the name of the reaction usually talks about the product, but that's not always the case. In one of the reactions in this chapter, it's like talking about the starting material, like it's called the malonic ester synthesis, but you're not making a malonic ester, you're starting with a malonic ester. So some of these names are confusing, but that is the general rule, which is not a great answer. It doesn't really help you, but that's how it be in chemistry. They hate us so much. Okay. So we're going to do this reaction that I'm only going to say once, and I'm not going to say it right. It's the Hels-Volhard-Zelinsky reaction. It sounds like a stroke. And we actually have 2 different versions of this reaction. So I'm going to draw it out on another page. Add page, please. Okay, so the Hels-Volhard-Zelinsky one. I probably didn't even spell this right, to be honest. Zelinsky. Sure. Okay, so we're going to have 2 different versions, like I said, and I believe I only drew one of them out in your handout. I don't know why that is, but add in this one that I'm drawing right now. So we're actually starting with a carboxylic acid this time. And we have Br2, and we have PBr3. So let's see who remembers from earlier chapters. What the heck does PBr3 do? I'll do a drum roll. It's a protecting group, yes. It makes acid halides. Yes, okay, so anytime you see PBr3, you're going from OH to Br, right? And as you guys said, it turns carboxylic acids into acid halides. So that's step number 1. And cool, now we have an acid halide. That's fun and dandy, right? What does Br2 do in this chapter? What happens when we have Br2? Exactly. So we're going to replace an alpha hydrogen with a bromine. So step 2, I drew way too big. There was no reason for me to draw this big, but that's fine. We replace an alpha hydrogen, and this time there's only one alpha hydrogen present anyway, or one alpha carbon present anyway. So we have to add a bromine here. And believe it or not, folks, but we are done with this reaction. Ta-da! That's it. I didn't do the pushing arrow mechanism because, quite honestly, it's not necessary. As long as you know this, you are good. The second way to do the Haloform reaction is, let's start out with the same starting material just for funsies. And we're actually going to have Br2. We're going to have PBr3. And we're going to have, sorry about that, H2O. The palm rejection sensitivity thing is quite atrocious for notability, if we're being honest. Alrighty, so again, please tell me, what does PBr3 do? PBr3 does what? Everybody. Yes, it turns the OH into a Br. So in the first step, we get bam, 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 bam. No, I'm sorry, that's too ugly. I couldn't do it. Bam. And we have an acid halide. Sweet. And then Br2 does what? Oh, excuse me. So yes, Br2 is essentially going to exchange the hydrogen for a bromine. So we get, in the next step, we still have Br here, and we exchanged a hydrogen for a bromine. And so now we have H2O left over. What the heck could H2O do? I'll give you a moment to think about it. Yes, it attacks the carbonyl carbon. Heck yeah. Okay, so this is a chapter 17 problem now, right? So we have H2O. This is our leaving group. This is our nucleophile. We get rid of a hydrogen. And so now we have bam, 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 bam. Br here stays exactly the same. But now we switched that red Br for an OH. So that's the difference between the two Zahalobliskinsky reactions. So the difference was really just the H2O. If there is no H2O, you end with two bromines. If there is H2O, you get a carboxylic acid and a bromine. Ta-da! Hold on, I'm holding on. That's not as funny when you're not in person, but whatever. Oh, okay, so the reason I'm sorry, one second. Hi, do you need this room or? Okay, cool. Sorry about that. I have no idea what's going on outside. Okay, so here it's just like what we talked about in chapter 17. So when we did that reaction, remember we identified the leaving group, we identified the nucleophile, and we're going to have to take off one of the hydrogens because if we had an extra H here, there would be a plus. So something would come back, such as, for example, Br minus, and that would take away this hydrogen, which would take away the plus sign. So since we're kind of doing it like the fast version of the reaction, we're not drawing every single step, we could just skip forward to neutral. Does that make sense? I know it's annoying when I do it like summary-wise like this, but whatever. All right, so if anyone has any questions, please let me know, but that was cool. So that is all we have for today. It is 3:52, so I'm going to let you guys go enjoy the rest of your day. All we have left over is the 2 other reactions for this chapter, and we might start chapter 19 depending on where Dr. West gets tomorrow, but I don't think we're going to go through chapter 19. And yes, of course you can see the halogenation. Okay. So I'm going to do it in 2 pieces so you can see this part and then the next part. Oh, okay. So I didn't know he's like firmly said 19 isn't on the final, but that's awesome. I didn't think he was going to get to it. Alrighty, so as always, I'll stick around for another minute or 2 if anyone has any questions, but that is all I have for you today. Have a wonderful day. Oh, so this is, I'm not even going to try to pronounce it. I will just show you so you can. I call it the Mike Wazowski reaction. Do with that what you will. Goodbye, everyone.